25,000 years before the present temperature. Temperature has yo-yoed over the ages as wildly as it does through any single year. Like natural thermometers, ice cores have recorded these fluctuations, which scientists can read by examining isotopes of oxygen and hydrogen in water trapped in the ice. These isotopes come in two forms, light and heavy. Light isotopes have regular hydrogen and oxygen, while heavy isotopes have either hydrogen with an extra neutron or oxygen with one or two additional neutrons. Since heavy isotopes precipitate out of the atmosphere more quickly than light ones, scientists can measure the ratio between the two isotopes to estimate the temperature at any given time. The data in this graph, gleaned from a core drilled in central Greenland, shows how temperatures have risen by more than 20 degrees Celsius (36 degrees Fahrenheit) since the height of the Ice Age 25,000 years ago. 12,000 BP, before present, rapid climate change. Ice cores have revealed that global climate, long thought to change only very gradually, can shift with frightening speed, in some cases in a matter of years. As this graph shows, one such jump occurred about 12,000 years ago, as the last glacial period, the Pleistocene, was giving way to our current warm interglacial period, the Holocene. Suddenly, possibly in less than 5 years, average temperatures, which were slightly cooler than today's, plunged by about 27 degrees Fahrenheit, returning the world to near glacial conditions. As the graph indicates, calcium levels tend to go up and snow accumulation down with temperature, which is estimated by comparing the ratio of oxygen isotopes in water, see temperature in core at left. The Younger Dryas, as this freak period is known, lasted about 1,300 years before it returned, just as abruptly, to the temperatures typical of the period immediately preceding it. 1167 AD, dating. Annual layers of snowfall in ice cores can be counted as easily as tree rings, allowing precise dating of events such as volcanic eruptions. Distinct annual layers stand out because, in snow that falls in summer, crystals are larger and acidity higher than in winter snow. In some cases, scientists can even tell seasons apart by using a laser to measure the concentration of dust particles. Winds are generally stronger in springtime, meaning more dust gets blown into the atmosphere. In this photograph of an ice core drilled in the Kunlun Mountains of western China, the thick, lighter bands indicate heavy snowfall during the monsoon season in the year 1167 AD, while the thinner, darker strips show layers of dust blown into the snowfield during the dry season. 1400 AD, see Storminus. Viking colonies in Greenland abruptly vanished toward the end of the 14th century. Why? One clue comes from ice cores. This graph, which combines results from cores taken in both Antarctica and Greenland, tracks sodium levels over the past 1,200 years. In colder periods, seas become stormier because of the greater contrast in temperatures between the tropics and the poles, and so more sodium, an indicator of sea salt, winds up on the ice caps. About 1400 AD, the cores at both poles clearly show a sharp rise in sodium, which some scientists say marks the onset of the Little Ice Age, a period of much cooler temperatures that lasted into the 19th century. For the Vikings, a series of abnormally cold winters in the late 1300s spelled doom.